For millions of years, humans held a monopoly on a very specific physical skill: long-distance endurance. While other animals were faster in a sprint, we were the only species capable of outrunning prey over hours of pursuit. Our bodies evolved as specialized heat management systems. We use sweat to regulate internal temperatures on the move, and our Achilles tendons act as energy-returning springs, allowing us to maintain a steady pace while other species collapse from exhaustion. Replicating this in a machine has been a decades-long failure. Most bipedal robots have been limited by the weight of their own power sources and a tendency for their electronics to overheat within minutes of intense movement. The physics of a two-legged stride is essentially a series of controlled falls. To run, a robot has to continuously calculate how to throw its weight forward and catch itself, a process that usually overwhelms real-time processors at high speeds. That technical ceiling was shattered in April 2026. A humanoid robot named Honor Lightning entered a sanctioned race and completed a full 21.1-kilometer half-marathon on two legs. Honor Lightning finished in 50 minutes and 26 seconds. It wasn't a simulation or a short burst demonstration. For the first time in history, a machine had covered that distance faster than the swiftest human on record. To hit 50:26, the robot maintained a 2.23-kilometer pace for 21 kilometers. This requires continuous dynamic balancing. In flight, sensors correct posture hundreds of times per second. Asphalt foot strikes send massive shockwaves, multiplying body weight and threatening to shear knee and ankle bolts. Honor Lightning relies on microsecond adjustments in its actuators to soften these impacts. By slightly varying the stiffness of its robotic limbs mid-stride, it can absorb the energy of the road without losing forward momentum. At world record speeds, bipedal movement is a high-speed physics problem where the smallest error in balance or timing results in a mechanical failure. The robot had to overcome two specific engineering barriers that usually ground mobile machines: the weight of the battery and the buildup of internal heat. This chart illustrates the power density problem. To power a 21-kilometer run, a robot typically needs a battery so large that the extra weight makes running at high speeds physically impossible. Honor Lightning solved this by increasing the efficiency of its actuators. By wasting less electricity as noise or vibration, it could extract more mechanical work from a significantly smaller, lighter battery pack. However, pushing electricity through motors at that rate generates extreme friction-based heat. In a machine with no sweat glands, this heat builds up rapidly inside the metal chassis. The engineers designed a thermal regulation system that uses the airflow generated by the robot's own speed to pull heat away from the motors. It effectively mimics human biological cooling, allowing the machine to run for 50 minutes without its components melting. By managing this heat and power density, Honor Lightning demonstrated that mechanical systems can now endure the same high-intensity stresses as biological runners. As Honor Lightning crossed the finish line, its stride was as precise as it was at the first kilometer. Its posture was rigid, and its movement showed no signs of the degradation we expect from a biological body. A human athlete finishing a world record run is at the point of physical collapse, experiencing labored breathing, severe muscle tremors, and a loss of coordination as the nervous system fails. This run proves that the technical barrier of robotic endurance has been bypassed. If a bipedal machine can outlast a human at record-breaking speeds, the constraint of short battery life and overheating in mobile robotics is no longer an absolute limit. This has immediate implications for search and rescue. A robot with this level of endurance can move through a disaster zone at a constant high speed, covering territory faster than any human first responder could on foot. In logistics and the military, machines can now be deployed across difficult terrain where they previously would have run out of power or failed due to thermal stress. April 2026 wasn't just a win for a sports team or a lab. It was the moment a machine officially took the lead in the one physical trait that defined the survival